All right, get this going. All right, it's been a while. It has been a while. Okay, yeah, I got to get back into the hang of streaming. It's been a minute. So this one's gonna be fun. It's gonna be short, but it's gonna be fun because I've pretty much got the design down. Because I didn't design it. I'll go through real quick what I'm gonna do, but um, yeah, I didn't design this. So I found a paper that is pretty interesting. It's interesting because I'll show it to you. It uses reinforcement learning, which is very popular in robotics, specifically humanoid robotics. Um, it's interesting because it approaches and solves a problem using reinforcement learning. Um, and so you take this pendulum and you swing it around, and you can actually stabilize it in four equilibrium points. So what I want to do is I want to recreate this, both mechanically and from a software standpoint. So I actually have the algorithm training in on my server right now. But in the meantime, while that works and I get that tweaked, I actually need to build this thing. So I'm going to design this thing from scratch, and we're going to do some light mechanical design to do that. I'm going to do this exclusively using Sencut Sen Parts 2, which is going to be cool. So we'll have a mix of some sheet metal and actually some CNC parts that they have. And so this is actually one of the equilibrium points. You have the top and the bottom link in line with the vertical. And it looks actually really crazy. It's very impressive, actually. And so they've actually got a video of this working. Yeah, they've got a video of this working, so I know it's possible. It's just a matter of actually designing this thing and getting it built. I've already got the motor on order. That's what you see here. So the only thing that isn't in CAD right now that I have to get is essentially the bearings and the encoder. So let's actually start with that. Let's actually get a look at the encoder. They actually use two types. I'm not entirely sure why they use two encoders and why they didn't use. I know why they used two encoders. You need an encoder for each axis. I don't know why they didn't use the same encoder for both of these axes. I have an idea. I have a suspicion in that mechanically it had to be that way, um, because of the. Let me open up chat real quick. I realized I forgot that. I realized that they might have had to do that because because you have to run cable or wires from the encoder through the parent axis. And so, for instance, this link here, if it's spun 720 degrees, you would bunch up the cable, and that would, or the wires or the cable, and that would destroy the cable. So I think that's why they switched to a magnetic encoder on one axis or the last axis, but they didn't do it on the parent axis. So I want to understand why that is. In the meantime, just to get the build going, I'm actually going to use the same encoder all around, and then I'll find out later if there was a reason that they didn't mention in the paper why they actually did that. But we'll learn through getting it wrong. And so I'm going to find that encoder now, which was this magnetic encoder. Yes, this one. Yeah, so we're going to go find this encoder. Hopefully the CAD is readily available. That's not it. The second pendulum uses this encoder. Thought this was a magnetic. This is a magnetic. This is the wrong one. this is the magnetic, I thought. So they've actually got it reversed. First pendulum is equipped with this encoder. By the way, an encoder, what it does is it just gives you feedback. It says, hey, I'm at this rotation on this axis, and that's used to fundamentally, it's used for the system to understand where it is and how it's working. If you didn't have the encoder, it would just spin around, you wouldn't know what's going on. So first pendulum. Is this it? 5 AMT 102. That's not it. Yeah. So this is the parent axis, the first axis. Is it magnetic? I thought it was. It's not. So it's this one. It's an AS 145B. Just got to find that. Here we go. I remember being pretty underwhelmed by the spec sheets on the website. So we might actually have to go to like Mauser or something. Let alone, I don't think we're going to find CAD. And they're not even showing a picture of the thing. That's a pretty chart. You know, it's serious when they give you a three-dimensional chart. You know, there's an engineer somewhere in that organization who really enjoys charts. Instead of splitting it out into two charts, they had one chart. Let's see, CAD. No CAD. That's going to be a showstopper. So is this information correct? This encoder it's almost like a Hall effect sensor where you have to pair it with a magnet. Contactless magnetic rotary position sensor for accurate measurement. Okay, so you actually have to pair a magnet with this, which is fine. So this is like a Hall effect sensor. So this is actually, this is interesting. So does this get packaged with a PCB, or do I have to package this into my own PCB? If that's the case, then we're not going to do this. I want to buy an off-the-shelf solution. I don't want to go do any hardware design. It sounds like this is not going to be something we can actually go use right now. Package. So this is just a this is actually just, this isn't going to work. I did not want to spend this stream selecting encoder. I really thought that this was going to be just download it and get it done. All right, this is a later us problem. Let's see if we can find a rotary magnet encoder that is already packaged that doesn't require us to do any electrical design. Something like this. This one. So this is what we want. We want it packaged and good to go. And I like Timken. They're a good company. Let's see if we can get a spec sheet on this. So where do you put the, so where do you actually put the magnet? That's the question. Cover magnetic target. Okay, that That makes sense. And so they actually give you the spacer. Okay, this is probably what we're going to do then. And how much does this cost? 90 bucks. That's a little pricey for what I wanted to do. I was hoping for 25, like the, I think it's a SIP. Is that the term? Okay, we're just going to use this. Let me see if I can pull this up on, can we buy this? Now is the question I should ask before I go design to it. Let's see. 1 second. All right, let's see. We can buy it. By the way, how frustrating is it as an engineer? For mechanical engineers and hardware engineers, they have to think about this. Let me take this off stream because I don't want you to know my email. Sorry, no offense. That before you actually can go do something, you have to see if you can actually buy it. It's not a question of whether or not it exists. It's a question of, will you let me buy it? How frustrating is that? It's like a daily, it's like 20% of my job. I'm not exaggerating. Okay. So we got the CAD. Drop that in. Perfect. Look at that. It's even got colors. Beautiful. Set screw. Don't like that. Could write a thesis on why you should not locate shafts with set screws, but that's for another time. Okay, so we got our encoder. So now we can actually get to what we wanted to do, which was some actual mechanical design. Let me not delete that. Let me save this. Do I have the part number in there? Because I can just grab this later. Actually, let's leave this open. We might need this spec sheet. That's not a spec sheet. That's an install. We still want that. We want the spec sheet. Give me the spec sheet because I need to know some things about you. For sure. Is that a spec sheet? It's not a spec sheet. It's got some useful information though. Finally, spec sheets, cable customer spec. No. So no spec sheets, just installation. That's fine. So actually, before we designed this, so we know we can buy it. I actually need to know that it has the correct not encoding, but CPR, which is roughly speaking how accurate it is. So it should be like, oh, resolution, that's what I meant. 1024. I don't know that is good. I think the paper had 4096 CPR. CPR isn't the same as PPR though. CPR and PPR might be different. And this tells us how many bits you have for 360 degrees. And that matters because it's going to drive whether or not this is accurate enough for this application. Let's see. To convert from PPR to CPR, multiply PPR by 4, which would be good. That would actually put us in the realm of what the paper had at 4096 CPR. PPR. Okay, so I'll just double check this. So pulses per revolution and counts per revolution. That's right. Yeah, so it's 4 times. Okay, so the paper had 4096, and we have an option for 1024, which is 4096, because that's 4. Yeah, okay. So this actually just happens to work out. Great. So now we've got all of this, and that's a lot of tabs. So I'm actually going to close this out. Actually, I'm going to leave this one because I think we might need that one. We will find, I'll just bookmark this. We'll get it later. Don't need this one anymore. Don't need that. We have a link here. Oh, before I forget, if you want to go see the code for the training algorithm that I built out based on the paper, you can actually go to this GitHub. So just go to my GitHub, and it's RDIP, the rotary double inverted pendulum repo. And it actually has all of the implementation for you to try out yourself. So this is using an RL algorithm that is beyond me currently. I do plan on learning more about it. It's a TQC implementation, truncated quantile something or other. Truncated quantile critics. So if you want to go try this yourself, you can actually go run the code here. I actually managed, so actually interestingly, this is a win. This paper takes, they said that it took them 2.4 days to train this. I think it was 2.4 days. Not to brag, but I got it down to 2 hours. If you can run it on GPU. They were running it on CPU, but you can actually parallelize it and utilize a GPU to actually speed this up. So, which has been critical in actually trying to get this to work, because it's taking a lot of iteration. Where do they talk about this? Is this the right paper? It is, right? No, this is the same mechanism. It's not that paper though. Let me find the right paper. Nope, I don't want to deal with you. Actually, let's see. Let's see if you let me in. Okay. Nope, this was in February. I'm looking for the one in May. This is the one? Yes, this is the one. Okay, this is the right one. All right. It's the same mechanism, so this wasn't for not, but the paper is different. I mean, the implementation is different, obviously. So I'll update the GitHub on that too. Okay, so real quick, why this is significant actually, now that I'm looking at the paper, I remember now. So it took them 2.4 days. Yep. I've been able to get it down to, I think, 2.5 hours. So I don't know. I'm really just wanting to do this on the mechanical engineering. The software isn't too interesting to me. I might go into the software later. If I get it working well, I'll go into the software and how I got the speed up to 2.5 hours. But I shouldn't gloat on that until I prove that it works first. Anyways, going back to why this is significant. So this is significant because typically in machine learning or in reinforcement learning, you try a bunch of things. When I say bunch, I mean millions or billions of iterations. And then you essentially throw away the ones that don't work. And the ones that do work reinforce the quote unquote agent or algorithm, you can tell I'm a mechanical engineer. It reinforces, it trains the network based on the failed attempts and the successful attempts. And then if you do that a billion times, you end up with a network that's trained to go do something, which for humanoid robots is standing up on its 2 feet successfully. What this has done is it's proven that, well, actually, you can do that. And instead of relying on, well, let me take a step back. In the trying all of this stuff out in humanoid robotics, what they do is they'll actually run this in something called a gym or a simulation off policy, I believe it's called, on a computer. So they simulate this using a simulated physics, and the robot like walks around and it looks goofy and it crashes a bunch. They use like Mujoko, I think. Yeah, so it over here in Isaac Sim or Mujoko, they'll actually simulate it like almost like a video game, and then they deploy it in the real world. Now, the reason why this paper is interesting is because they found it. Well, their sort of their abstract is that, hey, you can actually deploy the simulation in the real world without having to without having to do too much on the sim to real world implementation. Again, this is going beyond me. I'm a mechanical engineer. If you get the parameters right, so in other words, if you get the weight of the pendulum right, if you get the weight of the second pendulum right, if you get the friction coefficient correct, if you get all that right, all the distances and everything, it turns out you can actually directly deploy this with just some with a couple sample runs to reinforce those parameters. And so that actually is very interesting. And so I'm going to do that. To do that, we have to build it. So let's get back to that. Let's stop talking about something we don't know much about, which is software. Okay, so let's design this. So it's going to look kind of like this. I have my to-do. Let's get to design. Okay, so here's the motor. Like I said, I've already purchased it. It's on its way. Here's the encoder we're going to use. And I have some requirements which I'm going to set forth, which is going to be, it has to be safe. So we're going to build a polycarbonate enclosure around this thing. I want to package this all into one sort of system. They broke out the controller and driver off board. I would like to just have it in one sort of box that I can just carry around and deploy. I'm going to install it behind me. So that's my workstation or my workspace, or essentially my guest bedroom's bed with a 4x8 sheet of plywood on top, which has been my shop for a couple of years now. The joy of living in a city. And that's where it's going to get deployed. So we can start now on doing that. So the first thing is we need to build a frame. Actually, let's just run through the to-dos. So we need a enclosure, so frame / enclosure, package electronics. Just going to call it the frame. Is the enclosure, it's going to be what houses the electronics. I only want to implement one encoder, so I'm not going to do what they did in the paper. We just have a bunch of encoders. No reduction. So another thing I did was I actually ran through the calculations already to show that instead of using a 16-to-1 reducer like they did with these belt drives, I'm going to direct drive from the motor shaft and save myself a bunch of headache there. That required some torque calculation, but essentially what I did was I just upsized the motor by a factor of, I don't know if it was actually 16, but essentially motor torque is what drove, right? Because the speed doesn't matter as much. It's a DC servo, so the low speed behavior is going to be good. For an AC servo, I would consider that, but I ran the calcs and it's fine. It needs, I think, 3.5-ish Newton meters of peak torque, which it can do. It can spit that out pretty quickly. So no reduction. What else? Sheet and CNC mill only from Senketsen. They're sponsoring this. Thank you, Senketsen. Also sponsored by Shaper 3D, my favorite CAD package of all time. What else? Okay, let's just start with this. I think the frame is just a good spot. We'll find out a bunch of other stuff. So this is relatively small. I'm not too worried about the requirements in the sheet metal realm from actual manufacturing. I'm not too worried about that. Like I don't think the footprint's going to be an issue. Relatively speaking, if your sheet is within like 3 by 3 feet, you don't really have to go to Senketsen and find out what the maximum part size is. I would say 4 feet is where you start to worry a bit. So let's see, we're probably going to use 5052 aluminum, and we're probably going to start with 1/4 inch because the world runs on 1/4 inch aluminum. For the Euro engineers, that's I don't know, 14 million millimeters or something squared. Be funny if that's true. Actually, is that true? No, it's not. Okay. Maximum part size. Where are you? There it was. Max part size. No. There we go. B. Instant quote. 30 by 44. Yeah. So about 3 by 3 feet. That's about right. Put that aside. All right. Honestly, I'm not even going to sketch this out because we've got this right here. I'm just going to get going. I'm just going to get going. So let's get this out of the way. So let's look at the top view and set ourselves the 3 by 3 foot requirement, which is roughly, let's call it 800. 800 by 800 millimeters. And then constrain that. So here's our base sheet, which is already plenty big. I can already tell that that's too much. So we'll call it base width, and we'll make it square. We'll make this, I think 500 is going to be enough. 1/2 meter is plenty. So we'll change these to base width. Okay, why did that? No, that's right. Okay. So, and again, actually, we'll do sheet thickness 1. So thick 1, we said 1/4 inch, right? Which is, how many is that in Euro units? Man, I got a, yeah, 6.35. I know that intuitively, but I don't want to just say that without knowing it's right. Okay. And then we'll get the, actually, I want to set, one thing I've been doing recently, which I really like, is I've actually been setting my inner radius, my part radius standard. So I'm going to call this PR1, or actually PRI. Long story short, what I've realized is you'll have like a standard radius. So like, for instance, these are the outside of the part. Instead of just setting them arbitrarily to what I think is the right number, I've started actually parameterizing them. I've been making them parameters because I want to later change them all at the same time and just make it uniform. It's just good practice. So that's what I've been doing. All right, and so now we need to determine the height of the first stage, which is going to be essentially from here to here, which is going to be whatever the the minimum is going to be the height of this motor, which is 122 millimeters. We'll call it 200 for now. Yeah, we'll call it 200 for now. So actually, let me go back to this extrusion, make it one side, yep, and make it go the opposite way. So that way the world coordinate system plane here is 0, 0, 0 on the XY axis. And then we will pull that up 200, which is plenty of room. And we should also put we should actually put whatever this is going to be. So this is for any servo motor, you're going to find that they give you this mounting sort of, I don't know what you call it. It's just a mounting feature, but it's super accurate. And it's used so that you can accurately position this. So if you actually look at any spec sheet for a decent motor, they'll actually give you the GD&T tolerance for this. They'll just give you not the GD&T tolerance of like position or anything like that. They're going to give you a dimensional tolerance of plus or minus 100 micron or whatever that is, because that will actually be super critical in your tolerance stack ups later on. So if your motor sheet, spec sheet doesn't have that, I'd be careful. So that's going to be 70 millimeters. Nope, that's not 70. Okay, and why aren't you constrained? You're on the world coordinate system. Okay, and so we actually want that to fit, so we're going to give ourselves just a hair. I'm going to give it 50 micron. I'm actually kind of sure that Sencut is doing something on its tolerancing to enable parts to fit more often than not. I actually want to talk to them about this. But I've noticed that I've been conservative in my tolerancing, and I feel like it might be doubly conservative because they might already be doing something on their end to ensure that their cuts are always on the high end. In other words, your cutouts are always a little too big and they're never a little too small. I don't have any evidence for this yet, but so if we look here, we should see a 50 micron gap, and I think we do. Do we? Should be a small one. Yep, 50 micron. Well, it's actually technically 25 there, but no one notices. I'll hit it with some sandpaper if I actually really have to, which is embarrassing to say on stream. All right, let's cut out these holes. These are going to be, doesn't really matter. I think these holes are going to be oversized anyways. Why is my extrude not working? Oh, that was in another tool. I don't know what size these holes are. I'll look real quick after I pull this through. Okay. Whoops. Didn't hit enter the right number of times. Okay. These holes are 6. So we need M6 screws. So what's the total thickness? It's going to be from this part to this part. So we need at least, call it 25 millimeters. Why not? I think I've got 25s here anyways. And we want length to be 25. That's going to be a super standard screw. We want cheap, high strength, not plastic. They need to find a better way to just spit out. Yeah, I don't want to have to look through like brass. Who wants brass screws? I'm sure someone has a good reason, but I don't. Zinc plated 12.9 sounds plenty skookum. No threads because we're not psychopaths. Is this the right one? 265. It's 265. That's it. Yep. We'll need some nuts too. I don't use washers because washers are a myth. That is a joke, kind of, but I'm willing to argue most of the time you don't need a washer. Technically, this is aluminum. If you were actually to develop a torque spec for these screws, I would argue that you actually would need the dreaded washer, but most of the time, none of you are applying torque specs to your screws, and so you don't need a washer. And if you really want to know more about it, look up what a frustum is for a joint, and you will know why washers, you don't need them unless you're torque specking. So we are at 205, 205. Okay, so now we can import all of these, which we've done, and we're going to pull them out so we can get a good look at them. Pull that section back out. We'll get this hardware line. This might feel premature, actually doing this, putting hardware in this soon, but it's a habit that I've gone into earlier on in my career, which is because it's oftentimes you'll make a critical design decision without your hardware in the CAD, and then you realize very painfully, well, wait a second, I actually don't have the clearance I needed there. I had a multi-million-dollar slewing bearing assembly not work because I forgot to put the hardware in. So everything gets hardware now, even though it takes extra time. And that fits like a glove. Let's see if we can cheat this really quickly. Instead of patterning it, we will see if we can just rotationally do it. I think we can. I'm becoming a fan of using rotational patterns to just one-shot stuff like this. Okay, so now we've got our motor actually joined here. We'll adjust this height later. With that said, actually, let's get this controller into. I just want to put it in space. We don't need to put hardware through that right now, but I would like to just have it there. Oh, the vendor gave me a bad model. Can delete that. Well, why did that happen? Whatever. Deal with that later. It says 2 mounting screws. They are M2, it looks like. We don't really care too much. We'll just put this somewhere. I'm going to put it, first we'll align this. And then we'll place it. We actually want to, I think we want the connectors, do we want them facing out? No, I think we want them facing in. Yeah. The reason for that is because you don't want to be able to walk up to and accidentally bonk the thing and destroy the connectors. So we'll have them facing in. It'll be harder to work on, but it'll be more robust. Okay, and now that we've placed that, I also realized that we should also give ourselves some space away from the edge because we're likely going to be building out probably 4 corners of this thing. And looking at it now, I think we actually have some more room here. So actually, before we start ultra placing this accurately, let's go back to the sketch. And actually, we can do this parametrically because we are parametric people. Oh, 30 is too small. It's going to crash. That's my fault, not the CAD's fault. So let's try 300 on the base. It should work. There we go. Now I think this is going to package well. Do we have enough room with that motor though? Yeah, we should be fine. Should be fine. And then we'll probably bring this into center. So let's see, we are at, this is a ugly way to do this, but whatever whatever. So this is the mid plane here. I'm just going to measure that distance to the center. So center, so 128. I can move this 128. It should be roughly on center. There we go. All right, looks realish. And it looks like the cables come out of this side, which is good. It doesn't come out axially, so we won't have any issue with cables here crashing into the motor. Now, we're not going to add an encoder to this axis because the motor comes with an encoder, so I'm going to try and just make that encoder work before we start complicating the assembly. Real quick, I do want to add the bones for tying these two plates together, though. Actually, why don't we also, yeah, well, let's do that first. So going back to Senketsu, I'm actually going to be, I'm going to do something irresponsible here and actually use the CNC services for this one instead of using a tube. Because I think this is, the distance is, I think the part is small enough that it'll be okay. And it might get to the point that we care about tolerances, so we might want to just have that accuracy from the CNC process available. So CNC machining, looking for a maximum part size, which will be, oh, there it was. Oh, they have more than CNC. They have it for, do they add more materials? Okay, no, that's, they got to fix that. Maybe they have it inside of this. Yeah, here we go. Maximum 7 by 7 by 12. So 12 times 25 by 4. Yeah, that's plenty. That's plenty. So we have 300 and this is 200, so we have plenty of room. Okay. So what we will do is we'll probably, yeah, what's the best way to do this? We'll want bumpers on the bottom. We're already using M6 screws here, so let's try to use M6 screws everywhere. So why don't we do that? We'll add an M6 screw somewhere here. 6.1 because we want it to actually work. 15 just for now. We'll just start with this. Okay. And real quick, what is, oh, we want bumpers for this on the bottom. No, actually, we don't want bumpers. We're actually going to clamp this to the table. That's right. So how do we tie this together? How do we clamp that intelligently? All right, what we'll do is we'll actually tap these. Yeah, we'll tap these. Yeah, we'll tap these. So what's the tap size? From 6 by 1, tap size is 5. Look at that. Or drill size. Pre-drill size for the tap is 5. And I'm actually gonna, make this a body that I can boolean. Actually, yeah. Then I can subtract it. Okay. Now we can put in our, I don't know what we'd call it, our column. So how are we going to do that? I think we're going to just have a simple sort of, yeah, I think we're going to just have a simple like bar that ties these together. Make them 30 millimeters long-ish. Looks about right. I wanted to do that on another plane, I think. Actually, this will be fun. And we're going to actually pick up the outside of the plate. And the reason for that is because I want to locate these plates in a way that we'd actually build out a potentially a TA. I'm sorry, a tolerance analysis for this. So we'll do that. Can I redefine this plane to simplify the extrude? I think I can. No, I can't. It's fine. So I'm going to extrude this. To the bottom of this plate. Then we will, actually this was the right way to do it, yeah. Then we will boolean the, going to boolean the plates, but we're going to keep them. Which now you can see this actually locates this plate and this plate. Now we can do some lightning here. To do that, actually this is symmetrics. What I'm going to do is I'm going to create a midplane and model one side. Yeah, that'll be faster to do. So what I'm going to do is I'm going to lighten this. See, that hole's already there. I'm going to use the shell tool here, I think. So we want a thickness of, we'll call it a 1/4 inch-ish, so we'll call it 7. So that's the minimum. We actually don't need this, so we'll cut that out. We'll rejoin, and actually what we'll do is we'll pull this face out. Now, clean this up. Okay, so that's the minimum viable part we have right now. So we can actually mirror this back and boolean it. Great. So this is a couple things. The first one is it joins these two plates because we're going to put a screw through here on both sides. And then the second thing it does is it locates them using the outside of the plate. We'll want a little bit of clearance on that. So I'm going to go back before the mirror to edit the one side and add my clearance. So give it 50 micron. 500 micron is actually what I did, and I actually want it to be 50. Actually, this is a pretty large assembly, so call it 100 micron. We'll actually have to run a TA to make this feasible, but or realistic. This is good enough. Okay, so we have this part. It looks kind of ugly. Don't know why. I think it's the placement of that hole. I think we can put that hole in a better place. Let's find that sketch. Where'd it go? There it is. So we'll try 10. Really, this should be dictated by minimum edge distances. The plate is thick enough that I think we're okay, but there's a rule for that. It's like 2 times Depends if on the material. So for aluminum, I think it's like 2 or 2.5 times the diameter to the edge from the center. So this broke. It's probably my fault. Let's find out what it was. Yeah. Just fix this real quick. Oh, it's because these, I know what happened. That cylinder separated from the walls. That's all. Okay, so does this look silly still? I think it's okay. I wish Pete were here because he would have some good feedback on what the internal radii of this part would have to be. So I use a rule of, well, it really depends on how they're going to machine this. Here, let's just work on the one side for now. So PR, fill up this to PRO, I think we said. Yeah. Oh, and we have to get that offset back. Actually, I actually want to create a little bit of torsional stiffness. So I'm going to add a rib here, since this is technically an open section. That should reflect back. Yeah. So what is so technically it's 4 to 5 times no, it's the depth divided by 4 or 5 gives you the cutter radius for things like this. I believe that's the rule. So let's do that. And I'll talk with Pete later, or I'll double check the DFM stuff to see what that actually needs to be. So this depth is 33. So roughly 8 millimeter. The right way to do this is to actually look at end mills, but here we are. I know that they have ball end mills with 3 millimeter radiuses. So I'm going to default to 3 on that side and then go to 8 here. Ooh, we're kind of close. So actually we'll do 6. Close on that. We are going to be cutting it close to the screw head there, and we should actually add that just to be sure. Okay. And then let's add our hardware there so we can address that. Actually, we don't have to tap this plate now that I'm thinking about it. Yeah. We could actually just use, no, we do actually, because we're going to tap this so that way it can sit flush. So never mind, we do want to do that. Technically, we should probably use a flush nut there. Yeah, I'm just going to leave it the way it is. We'll deal with that later. Okay, so get this hardware in place. Copy on. All right. And then this needs to come down a bit. This will be smaller, so we'll go, I think 10 which should work. We just don't want it to protrude is all. I think, yeah, I'll have to go double check on hardware that really works, but for now we'll just make it work. And then when we go to sourcing, we'll figure out the rest. And then that mirrors down 2. Okay, so this is our standard detail that joins these plates together. We can now rotate this and pattern it. That's not a pattern. This is a pattern. Sorry if you're in chat. I'm not seeing chat for some reason. So if there is chat and I'm not seeing it, it's because I haven't done this in a while. I need to fix that. I'll figure it out next time. If no one is talking, then I will I'll know that it's not broken after the fact. One thing I'm noticing is this is the same nominal thickness, and we actually need to pick one of these surfaces to actually be the rest. Because they're never going to be spot on like this, like in CAD, obviously. So this is non-deterministic. We actually know which one of these 5 surfaces is actually going to sit flush. 1, 2, 3, 4, 5. So we're going to pick the columns to not sit flush. I mean, to not be the load-bearing members when you actually clamp this down. So we'll just pull this up a bit. So I'll step back in history before the mirror to do that, which is right there. So we'll pull this back 350 micron. We'll just call it a cool 13, and that should be fine. Yep, no, you're right. No chat. Good. Means chat works. I just haven't said anything worth commenting on yet. Okay, so now we have our column and our base and our motor mounting plate. And I'm realizing a mistake already. If you look at the paper, they had this on the edge so you can actually rotate the pendulum through, which means we actually need to pull this motor out so that way we can actually fit the pendulums around this thing. Also, I'm realizing why they're round, because this actually rotates. Duh. Cool. So we can quickly modify this to do that. I'm gonna just grab a snapshot of this. Come on. There we go. All right, I'm gonna grab just a snapshot of this and remove history. Okay. So we need to A, make this round, and B, rework these. So how will we do that? Let's actually go back and pull these planes back. All right, so this is what I'm going to do. I'm going to turn off everything we're not going to change. Okay, so now what we really need to do is find the... I see now why they kept the softboard. Because when you rotate these pendulums, you need clearance. Actually, what we can do is we can just make it taller. Yeah, we can just make it taller. Yeah, that's what we'll do. Okay. Everything's still working. We're fine. Although we should look at the paper and understand what the actual nominal parameters were. So we can model, roughly speaking, accurately to what they actually built. Yeah, you can see it actually working there. So I know that they gave the parameters for these things. So we want length 1 and length 2 here from the motor. That's really what matters. So where are the parameters? Here we go. Length 1, length 2. Where's L2? Save this. Actually go look at the paper and find out. what these dimensions are. Okay, so we want, yeah, L1, which is the nominal. No, it's not. Wait, did they not give us L2? They don't give us L2. Guess it doesn't matter in the modeling of the dynamics. Huh. So we get to choose L2. That's fine. So L1 is 164. 1645. Yeah. Yeah. No. Is that right? 1645. All right, we're going to have to just. So it's 165 millimeters long. Is that right? Yeah, that's right. Okay. Right now we have the distance between this plate is more than that, but we also have the length of the second pendulum. We're just going to make them all around, and I'll figure out. Yeah, we're going to just do what they did. We can offboard the electronics. It's not a big deal. It's just I would have liked to figure that out. Okay, so really what we want to do is we now have a design constraint. We want the circle to be as small as possible because that's going to reduce the rotational inertia about the z-axis. Yeah, I know I could use aluminum extrusion, but here's the problem with aluminum extrusion. If you used 80-20 like this, you can't locate the plates in plane with each other. Yeah. There's no, you can't, you'd have to mill the extrusion to get it to work. And because this is such a short distance, I'm actually okay milling these. So what is our minimum diameter? The minimum diameter is going to be set by the motor face, essentially. And we can pick it up there. So we'll sketch on this. That it looks like roughly 112, but we'll give it a little space and we'll go to, say, 175. Change this to intersect, and that's our new plate. Ooh, that's not right. And we're going to intersect with that body. So there's our new plate. My day job? I just quit my day job after I helped ship the 17 Pro. So I'm most recently I was a product design engineer at Apple. Thanks. I mean, something that complex, no one person takes credit for that. And honestly, I don't consider myself worthy of credit for that one. It's just such a complex thing. I would be skeptical of any one person who were to take credit or feel particularly positive about shipping something that complex. I mean, just think about how many engineers it takes to make something like that. It's just, you can't even fathom. Literally thousands. It's cool though. I need to get this in line. What's the best way to pull that? I guess a sketch. if the software doesn't work, you should complain about the software, the folks responsible for the software. That looks about right. Almost. Yeah, that's good enough. Okay, I'm going to slice this back to simplify this again. So we can mirror that over. And then actually we need to, yep, we need to keep that tool body. I'll say working on something, like working on a product that complex gave me such an appreciation for just the global just how, I don't know how to put this. This is going to have to change because we're interfering with that motor. How did we model this? Actually, okay, we'll make this new around. So actually we should sketch this to make it clever. So we'll pull out 38. Gives us some meat there to intersect and locate off this. I think we're okay. Gives us some clearance off of that. Let's see. Looks like enough clearance. Really should be more exact about that, but so which bodies am I working with? It's just this one, I think. Let's see. I don't want this one. There we go. So actually, this should be a function of thickness. So we need to know what is the distance here. It's no, that's not right. What is that? I guess we could eyeball it. It's not the right way to do this, but eyeballing never hurt anyone. Oh, it's, you know what it is? I remember the, well, no, I don't know the thickness, so actually we do need to eyeball this. Okay. So this will be IR1. Actually, we're going to, that's nasty. What do we do with that? This is, the team there is going to have a great time with this one. Actually, I'm starting to think this part looks stupid. Let's see. Let's see how stupid it looks. I don't hate it enough yet. I don't hate it enough yet. They're going to blast me on this, I think. They're going to have to 3D mill that. I don't think they want to do that. Whatever, we'll see. Maybe they're like, hey, this is great. We love 3D milling. And I'll say, you're welcome. Everyone's happy. Is this going to work? No. There we go. Okay. Okay. And remember, this was, I think, 3 we said? To get both sides at the same time before that mirror. Interestingly, if you do a stress analysis on this based on torsion loading, you're actually not going to... Actually, torsion loading, you might see this do some work. Oh, man, I actually don't know if that... Is that worth keeping around? Or should you chamfer it? Actually don't know the answer to that. So if this were a closed section, you do want to keep it, but it's an open section transitioning into a closed section. So it will, because the net torque is the same. Yeah, okay, I see now. Let me walk you through what I'm thinking. What I'm saying is, let's say you split this part. If you were to do a torsional stress analysis on this, you would have 2 sections at this interface, right? So essentially you've got this part and this part. And so at this interface here, you're going to transfer torque here to here, and then again from here to here. And so the stress is going to be some amount here determined by this geometry. And then the stress here is going to be determined amount by this geometry. So it's an open section here when you calculate the stress. The torque is, call it 10 Newton meters. It gets here, the torque is still 10 Newton meters. It's just that this section is stiffer. So this actually is better, but in the end, it isn't doing much because relative to this section and these sections, this is going to be like 90% of your torsional, what is it called? Torsional deflection, or I think it's torsional deflection. Your angular, what's the right term for that? Is it? I think it is torsional deflection. Yeah, torsional deflection of a shaft. Yeah, so 90% of it's going to be here because it's an open section, and then the closed section is going to be super stiff. All that to say, it isn't really doing much for me or for us, so we should really sort of ignore that and just go back to simplifying this part and getting rid of this. So we'll do that. Good question. So if this were global bending resolving into forces on the columns, I think I would agree with you. I think I would agree with you. Is the same true for torsion? Actually, I don't think I've thought of it that way. What do you think? Is that true? Does it resolve to just shear? I mean, let's think about it. So if we have 4 of these things, and I go to twist this shaft, twist this plate, it will result in shear 1, 2, 3, 4, all acting perpendicular. Or perpendicular? Yeah, perpendicular to, no, tangential to the effective radius of the member. So let's see. I think you're right. I think you are right. So let's call this the effective radius here. R RE. And it's really 4 times this because we have 1, 2, 3, 4. And then the net shear is going to be perpendicular to this axis, which is tangential to the surface here. So you get 4 shears. You're right. So yeah, global torsion resolves into local shear. Now the question becomes, is there local shear caused by something we're not thinking of? That's the question. That's a question. That's broken. We need to fix that. That radius is broken. Don't ask me how I know. There we go. Okay. So yeah, that's just shear. I think you're right. Real quick, the local torsion. Do we have local torsion? No, we don't, because it's a single screw. If you had another screw, say, like here, you could argue that you might develop some local torsion, but you won't really. So you're right. Yeah, it's shear. Good call. Okay. Let's get these fixed. So I'm going to grab a sketch, turn on wireframe. Okay. So we want to carry this screw hole through the plates. Actually, first, let's just change this geometry. And actually, it'd be awfully clever if that geometry is roughly the size of this control box. 200. So we'll call it 202. Yeah. Let's see if we can actually go back in history and change this real quick. Which sketch drove that? Is it this one? There we go. So let's change this to 202. Does that break everything? It doesn't break everything because that wasn't parametric now, I remember. Whatever. That's not what we're optimizing for. Minimizing that distance, we're optimizing for making it, optimizing for reducing rotational inertia about the motor axis. So we actually don't want to optimize for it looking better with this back plate. That's going to mount the control box. So I'm going to ignore the last 2 minutes. So instead, we're going to just pull these holes through. I'm going to use a trick that I learned recently because Shaper 3D lets you beautifully rotate and mirror surfaces. I'm not familiar with any other CAD that lets you do that. Okay, so now we got our mounting holes there, and actually we want those to be, so I think we said we were going to tap those. So we're going to bring this back a bit. We want them to be 5. That should reflect through. Yep. And now we will edit this plate. So we're going to slice it, and then we're going to slice it some more. Okay. Okay, we have our pendulum frame, which doesn't look that bad. Could be worse. It's going to be stiff. And then we want this. Let's just get this out of the way. We're going to figure out mounting that later. I see now why the paper authors didn't bother, because the dynamics of rotating this thing make it difficult. I'm also realizing now that we actually are going to arbitrarily use this dimension for the plate. Ugh. We're going to be fine. We're going to leave that. We shouldn't, though. We should do this correctly. All right. Let's see if we can do this correctly. So I happen to know this is going to be 45 degrees because we have 4 quadrants. So that's a good way to model this. Draw a circle out to that. Yeah, okay. And then we want a line that is perpendicular to these 2 circles. Do perpendicular. Actually, we'll just bring it to the center of the circle. And then this will become tangent to this. Wait, why aren't you becoming tangent? It's because you're not a circle? Okay. 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 I think that works. And then we're going to mirror this geometry. And then we are going to, what are we going to do? Actually, what is this diameter? Almost 190. Just make it 190. Okay. And so now, going to just rotate this around. Why didn't that work? Oh, the quantity is off. Okay. Is this plate the same? Let's actually, this was stupid. What I need to do is just work with the one body. Didn't need to do that with the sketch. So offset this just a hair. Is that right? It doesn't look right. Give it 250 micron. And then pattern. I think we can pattern this. Yes. We need to do this side too. Okay. All right. This is going to make sense in a second. We're going to get rid of that and we're going to just make this work and then bring that back up. Okay. So now, let's see, what, this is a 2 radius, so this needs to be a smaller radius so that it doesn't interfere, but do that in a second. So it needs to be bigger or smaller? I think it's bigger. No, smaller, I think. Because if this were 3, it would collide. Yeah, so it needs to be smaller. It needs to be 1, which they might not be able to do, but we'll find out. No, this is a CNC laser part, so they'll be able to do it. So never mind. So we'll make this 1. Okay, and that should not interfere. Perfect. We'll get this cleaned up. Make these OR. That looks stupid. Let's change that to IR. I mean, inner radius. Okay. And then simple design copy, we will, what was the nominal on this? I think it's from here to here, 193.65 plus 6.35. Yeah, okay, 200. Okay. We'll have this just, we'll keep this the same part. We'll reduce cost that way, even though we add more geometry and features, but we'll simplify that later if we have to. Okay, so the motor and the base are done, finally. Oh, we can actually get ourselves more clearance if we rotate the motor 45 degrees. That would actually be smart. So that way we're not so close here with this gap. So we'll do that actually. So what would change? It would be these holes would change. Yep. And then this motor would rotate. Yep. And then the screws would rotate. Hardware, I should say. Yep. Okay. Great. Look at that. Tons of space. That is the right way to do that. Okay. Should we chamfer this? No, because that is going to be impossible to mill, so we'll leave that. We'll just add a break edge note there. I just want that to be a nice clean sort of seat. And then this shaft is arbitrarily oriented, so we'll just rotate that back. Doesn't really matter, because that does rotate in real life. And that is now, yep. I'm glad we're modeling hardware because, thank you, yes. Direct modeling is the king. One thing we just did with the motor rotation here to increase clearance is that we actually have a spacing issue now with this hardware. They get around it by just using a mountain high amount of like gap between the motor mounting plate or the reduction assembly mounting plate and this pendulum assembly. But you can see now we can't just come straight off this motor. We have to build some distance now, which might not be the end of the world. And as a matter of fact, we do have to build a bearing assembly now that I'm thinking about it, even though we're not going to do reduction. Because the reason is because all motors, whether or not they tell this to you, come with an overhung load rating, which is to say, at some distance from the motor mounting plate, I'll isolate the motor to show you what I'm talking about. All motors, whether or not they admit it to you, have a rating, which is if you apply a load, in other words, the weight of an assembly or some radial load, P sub R, radial load, they give you a rating for this, and they call it an overhung load rating, OHL. Yeah. And it's really for like winches and things like this. But it also matters when you think about radial load caused by, say, spur gear teeth or whatever. Like that geometry always implies some radial loading. And so you're going to have some radial load. And so the way you deal with that is to say, look, I'm going to just design this assembly correctly and put a bearing here and here to decouple moment. So whatever I do with my load up here, PR, I actually don't care about this because really it resolves in the decoupled moment between my reaction forces and the bearings. Reaction 1, reaction 2. So we do have to use a bearing assembly, I think. Otherwise, we'd have to calculate what the overhung load max would be and then go figure that out. And that sounds like a lot of work, and it would be us cheating, which I'm okay with cheating, but I should, just so this isn't used in court against me in the future. I mean, I'm for cheating when it simplifies mechanical assemblies and it's not actually cheating when you do the engineering to prove that it works. That's what I meant to say. But we do have to rectify now this overhung load question, which might be simple enough. Maybe we can actually build it a secondary part that piggybacks off of this. Ooh, actually, I like this. What if we do this? So what if we build a part? So what if we move these screw heads up? I mean, these nuts up. Let's say we're going to use a very small but reasonable 3mm thick plate. What if we do this? What if we build like a little cup that comes in here? Yeah, comes in here like this. Houses our bearing. Here, I'll just draw this real quick. The perimeter. We have something like this. And our bearing in blue bearing, get it? Does something like this. I guess we need to have 2 bearings, probably. So we have to figure out how we're going to couple these. But this helps us decouple the moment that would have been applied to that load. And then we have a shaft in here that actually sits against the bearings. We have to figure, actually we can just gap this with how many colors do I have left? We'll just put a spacer in here. Maybe. Yeah, I mean, this isn't 100% what it needs to be, but yeah, something like this. Then we can pull this out. We can actually attach our pendulum here. And we decouple our moment there through the screws here. That might be what we do. We'll figure out what we're going to do with this encoder later. Okay, it's getting late. Yeah, it's getting late. I got to run. We'll pick this up next time. All right. See you next time. Thanks for joining.